All right, so today's physics lesson, we're going to be learning again some more about refraction, but this time we're going to focus instead of what happens when the change in medium causes the light to slow down, but what happens when the change in medium causes the light to speed up. And it basically amounts to the same thing with one extra little hiccup that we need to be careful about. All right, so here we go. When a beam of light strikes the boundary between two media, one of three things will happen. Here's the first thing that can happen. So first of all, if your beam of light is going from a low index of refraction to a high index of refraction, that is the same exact thing as saying from a medium where the light travels fast to a medium where the light travels slow, which is the same thing as saying a dense medium into a less dense medium. So all three of those things mean the same thing. So if your beam of light is doing that, then what happens is the light will reflect, so that your angle of reflection equals your angle of incidence, and it will refract. And when it refracts in a very specific way, which is it refracts toward the normal line. All right, and what that means then is that your angle of refraction will be less than your angle of incidence was. All right, and to figure out how much the light bends, you use Snell's law. All right, this is exactly what we did in video 9.6. All right. All right, to give you a visual, it's this. So what I've got here is a little laser beam, which I can turn on and off. All right, and it is right now shooting just through air. Okay, so my medium up here is air. The index of refraction for air is 1. Okay, and right now it's set up so that under my boundary here, so this line here is my boundary. Oops, BDRY boundary. So right now it's also air under the boundary. Now, if I take the index of refraction down here under the boundary and increase it so that somehow my medium down here is getting denser and denser and denser, the light bends. So watch what I'm going to do. I'm going to take this index and I'm going to gradually increase it. And watch what happens to my reflected beam of light, not my reflected beam, my refracted beam of light, this beam of light. Watch what happens to it as my index of refraction increases. Get rid of that. All right, so as the density increases, it bends. But notice which way it's bending. It is bending. This dotted line represents what the beam of light would do if it didn't bend. It's bending toward the normal. That's as normal. Okay? So that's what we've been talking about up until now. And it turns out that no matter what your angle of incidence is, your beam of light will always do two things. It will reflect and refract. Okay? So that your angle of incidence is equal to your angle of reflection, and then you have an angle of refraction that can be determined using Snell's law. So that is exactly what you did in video 9.6. It's what we've been doing for the last day or two in class. All right, so that is option 1. Option 1 is where you're going from a small index of refraction to a bigger index of refraction. Okay, so let's move on. Now the question becomes this. What happens if we go the other way? What if we go from a high index of refraction to a low index of refraction? In other words, from a medium where the light is going slowly to a medium where the light goes faster. Or from a medium that is less dense to a medium that's more dense. Again, all three of those mean the same thing. All right. When that happens, if the beam is doing these three things, then you must find what is called the critical angle. All right. The critical angle is the one specific angle of incidence which causes the angle of refraction to equal 90 degrees. Okay, so let me come back to this in a second. All right, let's go back to our little simulation here. Okay, so once again, I've got my laser beam shining just through air. You'll notice that both above and below my boundary right now, my medium is air. Okay. Just a moment ago, we looked at what would happen if you went from air up here into not air down here. Okay, so we're going from, last time we went from a low N to a high N. So now what happens if we go the other way around? So what I'm going to do now is this. I'm going to leave this bottom area to be air. So it's 1. Okay? And I'm going to take this and increase this index of refraction. All right, so this time, instead of going from a small index to a big index, this time we're going from a big index to a small index. All right, so again, I'm going to take this little slider here and I'm going to increase the index of refraction for my medium on the top. And watch what happens. This time, oops, the light still bends, but now it's bending the other way. See, look, this is where my beam of light would have gone if it hadn't bent, but this time it bent away from the normal. Okay, so that's what happens when you go from a big index to a smaller index. Okay, but the problem is there's a limit to it, because look what happens. So here's my scenario. So right now I've got an angle of incidence and an angle of refraction. But as you guys know, as your angle of incidence increases, so does your angle of refraction. So watch what happens. I'm going to start with, let's get rid of all this garbage here so the drawing doesn't get too cluttered. All right, so I'm going to start with the beam of light going straight in. So there it is. My beam of light is going straight into the boundary. My angle of incidence is 0 degrees. The beam of light just goes straight through. Okay, so watch what happens. As my angle of incidence gets bigger, watch the refracted beam. Right now, here's my incident beam. Here's my refracted beam. Oops, that's not what I wanted to do, sorry. Incident beam, whoa. Here's my incident beam and my refracted beam. And you can see what's happening is this refracted beam here is getting closer and closer to the boundary. And look what happens if I make my angle of incidence a little bit bigger. Oh, there we go. See that? How the refracted beam sort of disappears? So what happens is when you're going from a big index to a small index, if your angle of incidence is small, it refracts. But if your angle of incidence is very big, it doesn't refract at all. It just reflects. Okay? And it turns out the angle that is the dividing line between refracting and not refracting is called the critical angle. So for this example, it looks like if I put my angle of incidence right about, oh, sorry, I'm going the wrong way. If I put my angle of incidence right about there, this refracted beam is almost 90 degrees. Okay, so the critical angle would be this angle here, which caused my refracted angle to be 90 degrees. Okay? So, here are the other two options. Option 2 says if you're going from a big index to a low index, then find your critical angle. And then what you do is you compare your angle of incidence. If your angle of incidence is less than your critical angle, then it refracts and you use Snell's law. If your angle of incidence is bigger than your critical angle, then it doesn't refract at all. It just reflects following the law of reflection. Okay? So, what you need to do then is this. Find your critical angle. Okay? So here's how you find the critical angle. You basically start out with Snell's law. All right? But remember, the critical angle is the incident angle that results in an angle of refraction of 90 degrees. Okay? Now, it turns out that the sine of 90 degrees is just 1. So this just goes away, because NRA times 1 is NRA. Okay? So we get this equation. All right? Now, there are going to be problems in your homework where you'll know the critical angle, and then you can use that equation that I just drew an arrow at to find your missing index refraction. So use this if you know your critical angle, and then you can find either NI or NRA, whichever one you're missing. Okay? But more often, what will happen is you'll know your indexes, but you won't know your critical angle. So we can take our algebra here one step further and figure out that critical angle is, oops, I wrote that wrong, the inverse sine of NRA over NI. All right? So basically what I did is I divided both sides by NI and then took the inverse sine. Okay, so this is the equation, this one that I just wrote in blue, is the equation you use to find your critical angle. Okay? So what's going to happen is you're going to be given a problem. You're going to get to the problem and you're going to go, oh, this is a problem where my light is going from a high end to a low end. So I'm going to find my critical angle. Okay? Once you find your critical angle, then there are two possibilities. If your angle of incidence is less than your critical angle, then the light reflects, just like always, and it refracts away from the normal, so that now your angle of refraction is bigger than your angle of incidence. And again, you use Snell's law just like normal. Okay? So that right here, what I just underlined, would be this. And you can see here that here's my critical angle, right? And my angle of incidence is smaller than my critical angle. Right? My angle of incidence here is, oh look, I'll even pull out a protractor. Boom. Mr. Hecker cannot be stopped. All right, so there we go. So my angle of incidence here looks like it's, what, a little less than 20 degrees. And my critical angle is, it looks like about 40 degrees, right? So in this example, my angle of incidence is less than my critical angle, and so the light refracts with some angle of refraction, right? Okay. The other possibility then is this. So that was if your angle of incidence is less than your critical angle. The last possibility is this, if your angle of incidence is bigger than your critical angle. And in that case, the light will reflect, just like always, and it does not refract. When that happens, this is called total internal reflection. So going back to our little animation here, that would look like this. Get rid of all this red garbage here. Okay, so now if I take my angle of incidence and make it bigger, notice there's no refracted beam, right? This beam of light comes in and it never makes it out into the air, so it just reflects. That's called total internal reflection. Okay? So those are the three possibilities. All right? And to be 100% honest with you, at this point, you know everything that you need to know. That said, I know that some of you like to see examples. So if you think you're good, stop the video here. Make a note that you stopped at 1340 seconds or whatever we're at. If you are somebody who likes examples, I'm going to do 3 examples, which you can either watch or not. My suggestion is try the problems. If you get stuck, maybe come back and watch this video later. Okay? So we're going to do 3 examples. In example number 1, I'm going to use the indexes of refraction to find a critical angle. In example 2, I'm going to use a critical angle to find an index of refraction. And in example 3, I'm going to solve a problem from start to finish. Okay, so here we go. Example 1 says find the critical angle for glass in salt water. All right, so first of all, because we're dealing with critical angle, that means we must be going from a high index of refraction to a low index of refraction. So what that means is here, my 1.65 is my high index of refraction. So that's got to be my Ni. It's got to be my starting index of refraction, which means that we're refracting into salt water, which is a lower index of refraction. Okay, because we're going from high to low. All right, and then to find your critical angle, you just do inverse sine of NRA over Ni. So it's the inverse sine of 1.40 over 1.65. Type that into your calculator, and you get, type that into your calculator, and you get 58 degrees. Okay? So what that means is, if you're going from glass into salt water, if your incident beam is at an angle of 58 degrees, that's the dividing line between where the light reflects only and reflects and refracts. Again, if you want to see an animation of it, it would look like this. All right, so I didn't realize this when I wrote this example. Unfortunately, I can only make my Ni 1.6. In the example we just did, it was 1.65. But so that would be the glass. And then here's our salt water. Notice salt water is a little denser, so it's a higher index of refraction. Okay? And so what we figured out is that our critical angle is 58 degrees. For us, it's not going to be quite 58 because we have the wrong NI, but it's pretty close. So watch what happens. If my angle of incidence is less than 58 degrees, let me make a mark at 58 degrees. So this, theoretically, that should be my critical angle. Let me go over that in a different color. So there's my critical angle. So as long as my angle of incidence is smaller than that, it refracts. And as soon as I go past it, it just reflects, right? Okay? So there you go. All right, example number 2. We're going to do this one in green. A newly discovered gem has a critical angle of 46 degrees. Critical angle is 46 degrees when it is placed in jello, which has an index of refraction of 1.45. Find the speed of light in this gem. So we know that one of our ends is 1.45. That's for the jello. Oops, that is totally not how you spell jello. So what we need to do is we need to find the velocity of light in our mysterious new gem. All right. Now remember, we learned that n equals c over v allows us to, if we know n, we can find v, and vice versa. So to find the velocity of light, we're going to need to know n for our gem. Okay. And what I told you was, here in red, I told you, if you know the critical angle, then use this equation. So that is what I'm going to do. So here we go. Ni times the sine of my critical angle equals NRA. But the question is n jello my Ni or my NRA? Well, remember, because we're talking about critical angle, I have to be going from more dense to less dense. So the question is, what is more dense, the diamond or the jello? I'm sorry, the gem or the jello? The gem is going to be more dense because it's stone. Jello is less dense. So that is going to be my NRA. So here's what I get. Ni is the n for the gem times the sine of the critical angle equals 1.45. Okay, so solve it. Divide both sides by the sine of 45, or I'm sorry, sine of 46. And it gives you a 2.02. Okay, so that number there represents n for our gem. It is 2.02. So now to find the velocity of light in the gem, I'm just going to rearrange this equation. So you get c over n. So 3 times 10 to the 8th meters a second divided by 2.02 gives us 1.49 times 10 to the 8th meters per second. And there we have our answer, the velocity of light in our mysterious new gem. Okay, finally, let's do an example from beginning to end. All right, so here we go. It says a beam of light travels through quartz, and it tells you what n is for the quartz. Into ethanol, it tells you what n is, and it tells you the incoming beam makes an angle of 70 degrees with the boundary. What will the beam of light do and at what angle? So you must make a drawing. Okay, so here we go. You first of all want to draw the boundary between your two media. All right, I'm trying to get in the habit of always drawing my beams of light so they come from the top down. So our beam of light is going to go to the boundary. It's going through quartz. So that's going to be my Ni, because that's where my starting beam is. And then it's going into ethanol. It tells me the n for that is 1.36. Okay? Don't forget to draw in your normal line. And it tells you, right here, it tells me the incoming beam makes an angle of 70 degrees with the boundary. So that means that my drawing here is terrible, because this angle here is supposed to be 70 degrees, which means then that my angle of incidence is actually 20 degrees. So this is not at all drawn to scale. If I was more fussy, I would go back and redraw that. But all right, so that's what we know. So now what we're going to do is we're going to go back to our flow chart, the little process that we just walked through. So we need to make a note that we're going from a high n to a low n. So let's go back to our chart here. Let's see. Option 1 is only if I'm going from a low n to a high n. That was option 1. So option 2 is going from a high n to a low n, and it says to find the critical angle. All right, so I'm going to go back to my example, and I'm going to find my critical angle. So where can I do that? I'm going to do that over here. Critical angle is, you can biggen the screen here, it's the inverse sine of NRA over NI. So it's the inverse sine of NRA, which is 1.36, over NI, which is 1.54. Divide it, and you will find that your critical angle is 62 degrees. Okay, so that is that. So we found our critical angle. Now what we need to do is we need to take a look, and we have to go, all right, well, let's see, our incident angle is only 20 degrees. So for us, our incident angle is less than our critical angle. So that means we're at option 2A. Okay, if you flip back in your notes, you will see that option 2A is the one where your incident angle is less than your critical angle. And it tells you that you need to find your angle of refraction. So we're going to use Snell's law now. So I'm going to jump ahead a page, and I'm going to do this. Here's Snell's law. Ni sine theta I equals NRA sine theta RA, and I'm going to plug in my numbers. My Ni was the quartz. I think that was 1.54. Is that right? Yes. Times the sine of my incident angle, which was only 20 degrees, equals 1.36. Yes, for ethanol. Whoa. Times the sine of theta RA, and solve this. So 1.54 times the sine of 20 gives you 0.527 equals 1.36 times the sine of theta RA. Remember, get that by itself. That guy by itself by dividing by 1.36. And you get inverse sine. No, you don't. Sorry. You get sine of your angle is 0.387. Take your inverse sine of that number, and you get 22.8 degrees. So what we figured out then is that our beam of light is going to reflect at 20 degrees and refract at, what did we just say? 22.8 degrees. All right, so there you go. Now, if our angle of incidence had been bigger than 62 degrees, then it would have just reflected and you wouldn't have had to worry about this last step of finding your angles. All right, so there you go. Those are the three things that can happen, and an example, not an example of each of the three things, but three examples that are hopefully helpful. All right, happy refracting. I just said that. That's embarrassing.